In this video, I'm continuing the derivation of the probability continuity equation. So where I left off was we had rewritten the Schrodinger equation, or if we had taken the Schrodinger equation for psi, we had written out the complex conjugate of that to come up with a Schrodinger equation for psi star, and then we combine them, and what we're left with is this equation right here. So right away, we can say that the probability density is our familiar psi star psi. So therefore, we can write now the time derivative of the probability density is this part on the left-hand side. Okay, so what about the right-hand side? Well, in this one, what we want to do is we want to reduce it a little further into something more familiar. And so what we can show is that psi star del squared psi minus psi del squared psi star is the same thing as the dot product of the del operator with psi star gradient of psi minus psi gradient of psi star right here. So we can put that into the equation now. So now our equation is I h bar derivative of the probability density with respect to time is now minus h bar squared over 2m del dot psi star gradient of psi minus psi gradient of psi star end parentheses. Okay. Actually, before I go a little bit further, I'm going to divide both sides by I h bar just to get the derivative with respect to time by itself. So that gets rid of one of my h bars, and I put a I in the denominator. Like so. Okay. And all of these are constants. So minus h bar over 2mi are just constants. I can bring them on the other side of the del operator, and I can rename this quantity J. So very convenient name, which we're going to call the probability current. And that is h bar over 2mi times psi star gradient of psi minus psi gradient of psi star. Okay, so that's our probability density current, and so if we throw this in, then we reduce the equation to the derivative of the probability density with respect to time is equal to minus the divergence of the current, which is the exact same continuity equation we had for electric charge, and exact same equation we have for the continuity for most anything. But in this case, we're talking about the probability density of a quantum mechanical problem. So just to kind of reiterate, the probability density is the same thing we've always used, psi star psi. And the current is now this combination of psi star with the gradient minus psi with the gradient of the complex conjugate of it. And for the most case where the potential energy is real, this is always the current form that you can use. So if we figure out what the wave function is and calculate its complex conjugate, then we can calculate not only the probability, but we can calculate the probability current, how the probability is flowing from one place to another, and it follows our continuity equation. So this is kind of a very elegant solution. We're using results from classical physics. In this case, the example I used in the first video was classical electromagnetism, and the same conservation law, the same continuity equation now exists, and this can be used in basically almost any case for in quantum mechanics, at least right now, for when we have a real potential energy. We can calculate the probability current, as well as the probability density. So I'll stop the video here, and then in the next video we'll go over one of the exercises in Shankar's book, where we deal with a potential energy that is complex, and that has a real part and it has an imaginary part.